Thank you. All right, so we're going to talk about sequences of holomorphic functions. From some omega, which is an open set, into the complex numbers, of course. Okay. So, first theorem. Suppose Fn is a sequence of holomorphic functions that converge uniformly Let me write this and then I'll see what's happening. Uniformly to F on all compact subsets of omega. Then F is holomorphic. Okay, so I'm gonna... Okay, suggestions. Why do you believe this? So what are we going to apply? What are we going to apply Moirés theorem to? Yeah, so Moirés theorem is that if we have a ball and if we integrate every triangle on the ball, so again, every triangle inside the ball for some function f and it's equal to 0, then that function f is actually holomorphic. Yeah, that's Moirés theorem. So what are we going to apply Moirés theorem to? Well, we're trying to prove that f is holomorphic, right? Yeah. So if a sequence of fn that are holomorphic, all we know about f itself is that it's the uniform limit of these guys. We want to conclude it's holomorphic, yeah? And the suggestion is to use Moirés theorem, and indeed Moirés theorem would be a good tool for this, and we will try and use it for f, yeah? Because if we could show that for every triangle inside a ball, the integral of f around that triangle is equal to 0, then we know by Moirés theorem f is holomorphic, yeah? Okay, so first issue. We have just an arbitrary domain here, yeah? So let's just take some ball which is such that its closure is contained within omega. So pick... Ooh. Sometimes when I start to write, I start off writing the wrong letter of the word, but there's no B in pick, so that was very weird. So anyway, pick a ball. There is a B in ball, so that's maybe why. Pick a ball, B of R of Z0, whose closure is contained within omega. Okay? Like this. Then, for any triangle, T contained within the ball, B of R of Z0, yeah? Because we know that these sequence of functions are holomorphic, we know that the integral around the triangle of Fn of z dz is equal to 0. Yeah, this we know. This is Cauchy's theorem, the very first theorem. Yeah. All right, cool. So, and if we look at this thing, the integral around the ball of f minus Fn. Let me write this. Okay, let me write the z like this. Actually, let's do it like this. If we look at this quantity, f of z minus Fn of z dz. Okay. By this fundamental inequality, we know this is less than equal to the length of the triangle times the supremum over this triangle T of f minus fn. Yeah? This is one of the basic inequalities we know. And because T is a compact subset of our set omega, yeah, this thing is going down to 0 because f is uniformly converging, fn is uniformly converging to f on every compact set. Yeah? So this goes to 0 as n goes to infinity. Yeah? So that means that this thing in the limit is equal to 0. So the limit as n goes to infinity of this thing, well, since we take absolute values, t f of z minus fn of z dz is equal to 0. The absolute value is a continuous thing, right? So this is the same as the absolute value of the limit as n goes to infinity of t f of z minus fn of z dz. Let's break this up. This guy is not involving fn, so that's just equal to the absolute value of the integral of f of z dz minus the limit as n goes to infinity of tau fn of z. But we know that all of these guys here are equal to 0. So this is just equal to the absolute value of f of z dz. Yeah? So 0 is equal to this thing for every single triangle T. Yeah? So by Moreira's theorem, we have that. F is analytic or holomorphic, I should say, in this ball. And this ball's arbitrary. We've just taken any ball which is compactly contained within our open set. So we have that actually F must be holomorphic on the entire open set because it's differentiable at every point in the open set. Yeah? So as B R of Z0 is arbitrary, F is hollow on omega. Okay. Can you think of another theorem we could have used instead of Moreira's theorem? So what's special about this theorem? What's special is that we have information about the 0th order, about the difference between Fn and F. And we conclude something of first order about F that is actually differentiable. Yeah? Which is typically a very hard thing to do. So understanding something of 0th order from something of first order, that's something we can always do. That's a fundamental theorem of calculus, right? But going the other way, going from 0th order to first order, that's usually impossible. Yeah? But since this is such a special subject, since we have such magical properties of these things, how can we prove this theorem with another tool that allows us to go from 0th order to control first order? What tool do we have that goes from 0th order to controlling first order? Okay, maybe I leave that as a homework exercise. I'm going to ask you to try and prove this theorem without using Moreira's theorem. Use another theorem. And the hint is what I said. What tool allows us to go from 0th order to controlling first order? Yeah. Okay, so this theorem has a more sophisticated version where when we have the same hypotheses, theorem, under the same hypotheses, I don't know how to spell that either. I don't. Let's just abbreviate it. Under the same hypotheses, we have that the first order derivatives Fn converge uniformly to the first order derivative of f. On all compact sets. Okay, I'm going to raise the board. Think about this. Try and figure out how we're going to prove this. So with the same hypothesis, we have that the sequence Fn, which are holomorphic, are converging uniformly to f. Yeah? And then from that, we're going to conclude that actually the derivatives Fn are converging uniformly to f prime. And we know f prime exists because this theorem says that it does. Yeah? Cool. And think about what I just said about what would be another way to prove this. What special thing do we know about holomorphic functions that is generally not true for other functions, for general functions? Okay, suggestions. What tool might be useful? Okay, proof. Take a compact set pi contained within omega, right? Omega is an open set, so we know that. Let me just write it this way. So we know that the distance between pi and the complement of omega is bigger than 0. So by that I mean the distance between two sets A and B is equal to the infimum of Z1 minus Z2, or Z minus W, let's say, where Z belongs to A and W belongs to B. So if we have two sets, this is A and this is B. When I say the distance, I mean the smallest distance between any two pairs of points, one in A and one in B. Yeah? So since we have a open set omega, if we take a compact set within it, there is some non-trivial distance between the compact set and the complement. Yeah? By basic topology. Yeah? So let pi of delta be the set of z belonging to omega such that a ball of radius delta around z is contained within pi. So this is the set of points where we can contain a ball of radius delta inside pi, right? So it's something like this. Yeah, it's something like this. Yeah? See what I mean? And what we have is that this guy, if we take the closure of it, let us okay, so this set pi is compact, so it's contained within some large radius. So pi is contained within some ball of radius r around 0. And what we also know is that pi of delta intersect that ball of radius r is compact. If we take the closure, is compact. Let's just take the radius of 2r, just so that we are well away from it. in omega itself, in, oops, not pi, omega delta. Like this is compact in omega. So the only reason I do this is that if omega is unbounded, then omega delta might be unbounded, and therefore if I take its closure, it's not going to be compact. Yeah? But this guy for sure is bounded because it's compact, so it's contained within some large ball. I intersect a double-sized ball, yeah? And I'm going to take that thing. Yeah, this is closed by definition. It's also compact. I mean, it's also bounded, therefore it's compact. Yeah, and it's also definitely a subset of this guy. Yeah, it's definitely also a subset of omega because we're all the points which are clearly within omega by a ball of radius delta. Yeah, so this guy is a compact subset inside omega. Yeah, cool. So what we're going to do is we are going to try and show that the derivatives converge uniformly on, I did say pi, but I meant omega. Omega, like this. What we're going to do is we're going to show that the derivatives converge uniformly on our arbitrary compact set pi. And we're going to do that by looking at the behavior of Fn and F on this set here, which contains it. This set that contains it. And this is going to be the principle. So suppose, well, okay, let me do this. If we can show that for any holomorphic function capital F on omega, then the supremum over pi of capital F is less than the supremum over this set I've just created, omega delta intersect b of radius 2r. Oops, the supremum of the derivative like this, then we would be okay. Then we have to complete the proof. Why so? Why is something like this going to allow us to complete the proof? I should put a constant here, c, constant c. And the constant c will depend on our delta. Why would this allow us to complete the proof? Because what are we trying to do? We're trying to conclude that the derivatives Fn prime tend to F, yeah? Yeah? And what do we know? What do we know about the situation? Come on, what do we have? We have a sequence of functions Fn, right? What property does it have? Right, so we have something of 0th order trying to control something of 1st order, yeah? And this is exactly what this inequality is. So if we can show that for any holomorphic function, if we have some subset omega, there exists a larger subset where we control the derivative in terms of the function, the 1st order in terms of the 0th order, I claim that's enough. But why? Yeah, exactly. Yeah. Because we just let f be fn minus f, right? Yeah? Because if we do so, since this is a compact subset, this thing on the right-hand side gets as small as we like as n increases, yeah? We don't care what this constant is, doesn't matter, right? Because this thing gets as small as we like. So it would mean that the derivatives get to be as small as we like. Yeah? You see what I mean? Yeah? So all we need to do, all we need to do is to show that if we have any arbitrary subset pi, then we can find some compact subset like this, yeah, such that this is true, such that this inequality in the box is true. Now, for sure, we can contain pi in a set like this, right? Because, as I said, there's a definite distance between pi and the complement. So we can make delta small enough so that pi will be strictly contained within this thing. Yeah? 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 In fact, if we think a bit more about it, since there's a definite distance, this thing here is pi. This thing here is pi. Yeah? We could actually make it so that if we put a neighborhood, say whatever, an epsilon neighborhood around pi, make it a bit thicker, that thing will still be contained inside this. Yeah? Yeah? Cool. All right, so let's pick delta small enough so that I'm going to write n delta of pi, which means the set of the union of all the balls of radius delta around pi. So that this thing is actually contained within this thing, omega delta intersect the ball of radius 2r. Okay, I can find such a delta, I claim. Again, because we have a definite distance between the compact set and the complement of the open set. Yeah? Okay, cool. All right, so here we are in delta, yeah? We're trying to control the derivatives of our function in terms of the f itself, where the f, in terms of the f itself on this larger set. So this red set here, this red set, we're going to think of this as omega delta intersect the ball of radius 2r. Yeah? And this is pi itself. So how can we control this derivative for every z inside this set pi in terms of stuff over here? So pick, I don't want to use the word pick twice. Suppose z belongs to our compact subset delta. Yeah? Yeah? So how are we going to do this? How are we going to control? We want to control f prime of z. Yeah? How can we control f prime of z in terms of something which is not f prime itself, but actually something of lower order f? How can we control f prime in terms of f? Cauchy inequalities, Cauchy integral formula. Yeah? So Cauchy integral formula for derivatives is 1 over 2 pi I. Let's take a ball of radius delta, because if we take a ball of radius delta, we are still inside this larger set here. Sorry, it's still this larger set here, by the way we've constructed it. Yeah? So take a ball of radius delta around z, and then this thing will be capital F of zeta, and then zeta minus z squared d zeta, Cauchy integral formula for derivatives. Yeah. So we can take the absolute value sign around this. So I never remember the formulae. Well, okay, I remember the basic formulae, not inequalities. So I always get the Cauchy inequalities from the formula. So then this thing is 1 over 2 pi. And then it's the circumference of the circle, which will be speed 2 times delta, 2 pi delta. And then this thing on the bottom is just delta squared, right? So we're going to have over delta squared. And then we just have the supremum around the boundary of the ball of radius delta around z of our function absolute value of f. Yeah? So we have a lot of cancellations here. We have the pi's cancel. So this is just supremum or 1 over delta supremum of, that's looking too messy, let's write that better. It's just delta to the minus 1 of the supremum of around the boundary of the ball of radius delta around z of capital F. Yeah? And since by construction the boundary of the ball of radius delta around z is contained within this thing, so actually I want to have that, I want to insist that the closure of this thing is contained within this thing, which I can do again for the same reasons. So this thing is less than delta to the minus 1, the supremum over this set, omega delta, intersect b of 2r. Let's take the closure because it's even bigger, capital F, like this. Yeah? Cool. All right, and that's true for any z inside pi. Yeah? That's true for any z inside pi. Yeah? So the supremum over pi of capital F prime is indeed less than delta to the minus 1, the supremum over this set of capital F. Yeah? And that's all we need, because again, we just apply this to fn minus f. Yeah? Fn minus f is a holomorphic function. Yeah? So for f equals fn minus f, we take the limit as n goes to infinity of the supremum over pi of fn prime minus f is equal to 0. In other words, they converge uniformly on compact sets, exactly as claimed. Huh? So the magic is this incredibly powerful thing we have of being able to control derivatives in terms of the function itself. The exact reverse of what we can normally do. Yeah? Yeah. All right, let me ask you this. Suppose we're not doing this for holomorphic functions. Suppose we're doing this for functions on the real line, on an interval, say. We have a sequence of functions fn converging to some f. Yeah? Is it the case that we can show that the derivatives of fn will converge to the derivative of f? And as you can guess, the answer is probably no, but I want you to tell me a counterexample. I want you to think of a counterexample. So think of a sequence of functions converging to some function f uniformly on compact sets. In fact, take it uniformly in the entire interval from, say, 0 to 1, such that the derivatives are not converging uniformly. I'm going to raise the board. Tell me the example once the board is erased. I've also understood how I can make the speed position metaphor. So let's think of it this way. If you have a car whose top speed is 70 miles an hour, then you can say definite things about its position, right? You can say that if you're on position A at time t, then at time t plus something, the furthest away you can be is position whatever, yeah? if t is 1, the furthest away you can be is 60 miles away from position A. Yeah? If t is a half, then it's 30 miles away. Yeah? So if you know the speed, you can say definite things about the position. If you have a control of the speed, you can say definite things about the position. However, suppose you have a car and you can control, or you can bound above its position or bound below, put its position in some bounds. You can force your car to be between some position point A and some position point B, which is whatever, 10 miles away. And you have complete control. The car always has to be between these 2 points on the road. Yeah? Maybe it's whatever. Maybe it's a long road, but it's always between these 2 positions. Yeah? From that information, you can't say anything about the speed, because you can drive your car from A to B as fast as you like and still be within that control between A and B. Yeah? So you can restrict the position of your car to something and have no control on the speed. Yeah? But if you control the speed of your car, then you greatly restrict the position. Yeah? You can say things about the position from knowing things about the speed. From knowing restrictions about the speed, you can't say any restrictions about the speed from knowing restrictions about the position. Yeah? Okay, cool. All right, now back to my question. We have a sequence of functions on an interval 0, 1 converging uniformly to a function f. We don't believe that the derivatives will converge uniformly to the derivative of f. Give me an example. Don't have to give an explicit example, just describe an example. Describe how that would fail. Yeah? So let's insist that our limiting function f is smooth. So we have a sequence of functions fn tending towards a limiting function f. Let's make it be smooth, even analytic. Let's have a Taylor series for f. Make it as nice as you like. Yeah? Try and either conclude under these hypotheses that we can uniformly control, we have that on compact subsets, the derivatives tends to a derivative of f, or tell me why it's false. Find a counterexample why it's false, or describe a counterexample. That'll be your homework problem. Okay? Cool. All right. So, I think that's it for sequences of functions. Now let's get on to the next main topic, which is meromorphic functions. Zeros and poles. Okay. Let's talk about zeros first. So, given holomorphic f and z belonging to omega, such that f of z0 is equal to 0. This is called a zero. We've seen these before. Is called a zero of f. Okay, and we've learned some things about zeros, right? We've learned that if we have a collection of zeros inside our domain, then any cluster point can't be inside it. Yeah, yeah. Unless the function is identically equal 0 on that set omega. We're assuming omega is connected. Yeah. Cool. So we know some things about this guy. So that means that zeros are isolated, right? So if we have a 0 inside our set omega, then there isn't another sequence of zeros. There is some ball where there's no other 0 around it. Yeah? Since otherwise it has a sequence of zeros converging to it and the whole thing is equal to 0. Yeah? So zeros are isolated. So we've learned that zeros are isolated. If f is non-trivial, zeros are isolated. Now let's describe what singularities are. So we say f has a singularity sing singularity at some point, let's say Z1, if and only if f is holomorphic on the punctured ball around Z1 for some bigger than 0, but not necessarily defined at Z1. This is a star here. I think this is a star on the circle. I think we did define this. This is the set of Z such that 0 is bigger than zeta. Set of zeta such that Z minus zeta is bigger than 0 but less than R. So it's everything in the ball but not equal to the center point itself. So if f is holomorphic in the punctured ball for some small radius, but not necessarily defined in the punctured ball, defined on the actual value Z1. And there's various ways it can be failed to be defined on Z1. For example, if we have f of z equals, say, z squared minus 1 over, say, z plus 1, yeah, then what do we know? Then f of 1 is not defined, means nothing. Oops, not f of 1, f of minus 1. F of minus 1 is not defined because at the moment it's just 0 over 0. Yeah? But this is not so much of a problem because you've seen this from calculus lots of times, right? We do this. Right? So if z is not equal to minus 1, yeah, then we can cancel the top and bottom. Then f of z is actually just equal to z minus 1, this nice function. Yeah? Yeah? So we can actually just actually fill this hole where the function is not defined and create a function that is holomorphic, right? Yeah? So we can define let's call it f tilde of z to be equal to this guy here, z squared minus 1 over z plus 1 if z is not equal to minus 1, and then just equal to minus 2 if z is equal to minus 1. Yeah? Yeah? And that's exactly the same thing as just being z minus 1 for all z. Yeah? So that kind of singularity is pretty harmless, right? Yeah? This is a harmless singularity. And these do occur. This is a very natural expression. This is just a rational function. And sometimes it turns out that the singularities that seem to be there are just not important. We call them removable. So removable singularity, you can remove it, and then we have a nice holomorphic function there. Yeah? So it's a removable singularity. Yeah, these are the guys you can basically forget about. Another example. We could have f of z equals 1 over z to some m for m bigger than or equal to 1. Okay? Then f of 0 is not defined as a complex number unless there's a way to actually add infinity to the complex plane where it makes sense, but that's not what we're going to do for the time being. So as a finite complex number, this is not defined. We have a singularity here. Yeah, we have a singularity here. Then f is f can't be just, you can't make a small change to f and just get rid of the singularity. This is a part of this function. This is real. You know, this guy we can't just ignore. Then if is singular at 0. Yeah, that's a serious thing. However, it's somewhat predictable the way it's singular, because what's happening as we go towards 0, it's going off towards infinity, and it's going off towards infinity in quite a regular way, in quite a standard way. Here's another example. Suppose we have f of z equals e to the 1 over z, like this. Let's think about this guy. Then it's perfectly fine. It's holomorphic everywhere except 0. Yeah. So oops. But at 0, it's got a singularity. It's not defined. And I claim that this guy is very different than this guy. This guy has got a singularity that is much more dramatic than this guy. So I'm going to raise the board. In the meantime, I want you to think about the kind of singularity, what the nature of the singularity is, how this guy behaves as we approach 0, and then tell me about it when the board is erased. Huh? So start by thinking about what does the function e to the z do, yeah? and then put that together with what you know 1 over z does. Yeah? All right. This is our function. F of z equals e to the 1 over z. Tell me about the kind of stuff it does as we approach 0. What does it do? Let's think about what e does. Right? So what is e? So if we have the strip from pi to minus pi, then z goes to e to the z. What does it do? That's the same as x plus iy goes to e to the x plus iy, which is e to the x, e to the iy. Yeah? So what does the exponential function do to this strip? What does it do to the strip? We talked about this. What does the exponential function do to this horizontal line like this? So if you have a horizontal line like this, then the y is fixed, right? And the x varies. What's happening if we plug that into this? You just get a ray, yeah? It'll just give us a ray coming out with this angle like this, yeah? Where this angle is y. What about if we do something like this? So now the x is fixed and the y is changing. It's going to give us a circle, yeah? Yeah? And what will the radius of the circle be? If this thing is x like this, then the radius of the circle will be e to the x, yeah? Yeah? Well, this thing is e to the x. Okay, so what does it do to the strip? What does the e to the x do to the strip? Yeah, it wraps around the entire complex plane. Does it hit everything in the complex plane? It doesn't hit 0, right? So it wraps this entire strip around the entire complex plane except 0. Yeah? And what does it do to the strip above it? The strip from pi to 3 pi. What happens with that? Same thing, right? Same thing. So all of these, we can cut the complex plane into all of these disjoint strips, and each one of them is going to get wrapped around the complex plane. Yeah? Yeah? Pretty wild function, yeah? Even though it's easy to define, it's holomorphic. Somehow it's able to do that, yeah? Cool, all right, so that's a little recap of e to the z. Now tell me about this guy. What is the nature of the singularity at 0? Is it the case that we have to approach infinity as z goes to 0? Is it the case that we have to go to infinity as z goes to 0? Is it the case that we can go to infinity as z goes to 0? That's a simpler question. Can we go to infinity as z goes to 0? Here is 0. Let's approach 0. What kind of stuff can happen? What if we approach 0 like this, going like this? We're going along the positive real numbers towards 0. What happens then? Come on. Just goes to positive infinity, right? Because if it's a positive real numbers, right, then this thing just becomes e to some incredibly big positive real number, yeah? So it just blows up to infinity. What about if we go like this? So if we have a very small negative number, yeah, and we put it into this, yeah, we'll have e to a very negative number, right? So the approach is 0. Yeah? Cool. All right, tell me other stuff. What happens as we go down like this towards 0? How many times do we circle? What radius is the circle, for one thing? The radius is 1. How many times do we circle as we go down towards here? Infinitely many times, right? So if we have f of alpha times I, then that is e to the 1 over alpha I, like this, yeah? And what is this? That is just something of radius 1, so that's the same as e to the minus I over alpha, like this, yeah? And that is the same as cosine of minus 1 over alpha plus I sine of minus 1 over alpha, like this, yeah? So as we go down towards 0 with alpha, this thing is rotating round and round, yeah? And it actually rotates round faster and faster and faster. Yeah? We're going to do infinitely many times rotating around as alpha goes to 0. Do you see what I mean? Yeah, because alpha goes to 0, then 1 over alpha is going to infinity, so we're going along all these oscillations of the sine and cosine, yeah? We're going round and round and round and round the circle infinitely many times. You see what I mean, people? Give me a thumbs up if that makes sense. Yeah, cool. Yeah? And the same if we approach from this direction like this. It's going to go round and round. Yeah? Which is really, really crazy behavior, right? So it's analytic. It's got a Taylor expansion everywhere except at 0. Yeah? So you might think it's so nice outside of 0, it can't do anything too badly at 0. Yeah? But you're wrong. It does absolutely insane things at 0. As we approach 0 from this side, the function is wrapping around and around and around and around the circle more and more times, infinitely many times, faster and faster. Yeah? As we go on this direction, it blows up to infinity. As we go in this direction, it's going down towards 0. Yeah? So there's a whole variety of different things this thing will do as we approach 0 from different directions. Yeah? So it's a dramatically strange and weird behavior here. Yeah? And as we do some kind of line going in some direction, we get some combination of these behaviors. Yeah? So you can spend a long time figuring out all the possible weird behaviors that you can get out as you approach 0 from these different directions. There's a whole zoo of different behaviors at this particular singularity. Yeah? It's just really sort of weird because it's so easy to describe, to write down, but it contains a whole massive amount of different information about how it's behaving as we approach 0. So this is a very different kind of singularity than the previous singularity of 1 over z to the m. Yeah? and certainly very different than removal singularity. Yeah, this is dramatically harder to understand behavior. Yeah? And this is what we're going to call, well, this is an example of something called an essential singularity. So this is an essential singularity, which we'll define later. This is a kind of warm-up of the kind of things you're going to see. So when we talk about singularity, we're going to have three types. We're going to have removable singularities, which are basically like things we don't have to care about. We're going to have poles, which are singularities that definitely exist, and there's no getting around that. But they behave in a very predictable way, in a way we can manage. And then there's these guys that behave in an insane way, completely insane way. And these guys, we can't manage, we can't do anything with them. We can't control the function, we can't understand the function around these guys. We can prove some theorems about how wild they are, but when we have a function with essential singularities, many of the things we'd like to do are much harder. This is singular. Cool. All right. So that's what we're going to learn about in this section. And let's start by discussing more the kind of things we can have as zeros. We're going to first learn about zeros, and then we're going to use that to learn about the second kind of singularity, the one where we have a consistent blow up. All right. So first theorem. Suppose f from omega is holomorphic and f has a 0, z0 belonging to this thing. Then there exists I should say, suppose f is holomorphic and non-trivial. So non-trivial means not identically equal to 0. There exists some n and a holomorphic function G, which is defined in some ball around Z0 of radius r, which depends on the function and the singularity, where G is non-zero at Z0, and we can write that f of z equals z minus z0 to the n times g of z inside this little ball around z0. In other words, we have a way to represent the behavior of the zero very, very well. Yeah? Because for very, very small, for z, which is very, very close to z0, this is a holomorphic function, which is non-zero, so it's tending towards its constant value, g of z0. Yeah? So what this says is that morally, the zero is an awful lot like just z minus z0 to the n. That's encapsulating the real behavior of the zero. Yeah? That's encapsulating how this thing goes down towards zero. Yeah? That's what this says. Okay, proof. All right, so it's holomorphic. It has a 0, but it also has a Taylor expansion around Z0. Yeah? So take the Taylor expansion. So we have that f of z is the sum. The sum from what? Where should I start? Well, since it has a 0 at z0, right, there's no constant term. Yeah, so I should start from, let's call it k, from k equals 1, potentially, right? Because for sure there is no k0 term. But actually, if we think about it a bit longer, there might not be a k1 term. Yeah? There might not be a k1 term. Yeah? There might not be a k2 term. Yeah? There might not be a k3, there might not be a k4, right? So this is for z inside some small ball around z0, the radius of convergence of the series. But if the function is non-zero, then there will eventually be some non-trivial term. There will eventually be some non-trivial term. Yeah? Because if all these Taylor series, all the terms of the Taylor expansion were equal to 0, then it says the function is identically equal to 0 in this ball. Yeah? So by the previous stuff, if omega is connected, that means the entire thing is 0. Yeah? So by default, we're always going to be talking about connected set, because when we have disconnected sets, we can just talk about the holomorphic function in each individual component. Okay? Yeah? So we've got to have that at least one of these guys is non-zero. Yeah? Yeah? So let n be such that, well, let n be the smallest integer such that the coefficient is non-zero. Smallest natural number, even not even integer. Okay, integer. So that means we have this expansion now. F of z is the sum from k is equal to n to infinity, ak z minus z0 to the k, and then you can guess what we're going to do. We're just going to factor out this z minus z0 to the power n. Yeah? So that's equal to z minus z0 to the power n, like this. So strictly speaking, if you want to be very careful, this is the limit of the partial sums, but on the partial sums, we can factor this out and then take the limit. So we can validly pull out this factor z minus z0 and write this. So k is equal to n to infinity of ak z minus z0 to the k minus n. Yeah? And then we just define g to be what's left here. So let g of z be this thing, sum k equals n to infinity ak z minus z0 to the n, to the k minus n, like this. And then that has the property that g of z0 is just equal to an, because all the other terms will vanish, right? So for k is equal to n plus 1, then we have an plus 1 z minus z0, that vanishes when we put z equals z0. No? Do you see what I mean? Okay, cool. So g is a nice holomorphic function, right? Because it's defined by the Taylor series. You know, it's got the same radius of convergence. This is good. You know, we've learned this. It's very nice. Yeah, and indeed, it's non-zero. So that exactly gives us the decomposition that we asked for. That exactly gives us the result that we asked for. Yeah, cool. So this is a very useful result because it means whenever we have a zero, we can really know the essence of the zero, and the essence of the zero is just this part here. Yeah, and the zero is a point where the function is going down to zero in a very controllable way, in a very regular way. Yeah? Which again is completely false if we weren't doing complex analysis. If we have a function from R to R, then the zero can be going down. The zero could be such that we go down to zero in any kind of different way, right? So for example, if we can have this, right? We can have f of z or f of x on the real line. Let me just specify in the real line. So on R, we can define f of x to be absolute value of x to the alpha for any alpha bigger than 0. Yeah? So it could have alpha as a half, right? So that means we're going down to 0 at this rate of the square root, right? So it looks like this. Looks like this. should be symmetrical, but it looks like this. Yeah? We go down to 0. So we can go down to 0 with any power of for any number which is bigger than 0, or even 0 itself, identically 0. Yeah? Whereas this thing says we're going down to 0 at an integer power. Yeah? We're going to 0 in a very, very nice, understandable way. Yeah? Cool. All right. I'm going to erase the board, and we'll do some more of this. I'm going to try and a pole of function f at z0 is where the function 1 over f has a 0. At z0. Okay. And so 1 over f of z is of the form z minus z0 g of z for some holomorphic function g defined in some ball around this, perhaps very small. Yeah. So then we can turn that around, and I should also add, and g of z0 is not equal to 0. So unwrapping this, we have that f of z is equal to z minus z0 over g of z. That's not what I meant to do. This is the power n, and this is the power now minus n. Let me write it like this. Okay? And g is again holomorphic, and it's non-zero at z0 itself. Since it's holomorphic, we can make the ball sufficiently small so that this thing is never equal to 0 in the ball. Yeah? So that means the function 1 over g is actually going to be holomorphic in this small ball as well. Yeah? And if r is small enough, then 1 over g of z is non-zero. So again, g of z is non-zero in the ball. So 1 over g of z is holomorphic, because again, it's just differentiable, quotient rule. We can differentiate when it's non-zero. And that too has a Taylor expansion. Yeah? So 1 over g of z has a Taylor expansion around z0. It's going to do the sum from k equals 0 to infinity bk z minus z0 to the k. I should write and so. Yeah? So putting this together with this thing, call this thing star, we have that f of z is z minus z0 to the minus n, and then this thing, sum k equals 0 to infinity bk z minus z0 to the k. Yeah? And when we pass this stuff through, the sum from k equals 0 to infinity bk z minus z0 to the k minus n. Yeah? And then what's that going to be? That's going to be the sum from k is equal to 0 up to n minus 1 of this thing, bkz minus z0 to the k minus n, and then the sum from k is equal to n to infinity of bk z minus z0. Yep. Z minus z0 to the k minus n. Yeah. And if we look at this part, then this guy right here, since k is going from n to infinity, yeah, this part right here is a nice holomorphic function. Yeah, the first term is a constant, the next term is z minus k to the power 1, and so on. So this part here is nice holomorphic function right here. So this guy is good. Yeah, and the singularity part, it'll be this part right here, where we have these powers from 0 to n minus 1. Yeah? So for every non-zero coefficient bk, we're going to have a singular part right here. Yeah? Yeah? So that means that we can actually write something that has a pole like this. So rewriting things, we can write it like this. If the sum from k is equal to 1 up to n of, now we're going to call these coefficients something else, just a to the minus k over z minus z0 to the k, like this. This will be the singular part, and then let's rewrite these coefficients. Then this will be the sum from k is equal to 0 to infinity, because the first guy is at 0, ak z minus z0 to the k. Yeah, because we can just relabel these coefficients, and these are the same powers of z minus z0. And this way we have the coefficients. We have the coefficients a to the minus n, a to the minus n plus 1, dot, 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 all the way up to a to the minus 1. These are the coefficients of this part, which produces the singularity. And then we have the nice part, a0, a1, a2, a3. That's the nice part that, is the ordinary nice Taylor series we have when we have a holomorphic function inside the ball. Yeah? So this part is the part that really defines a singularity. Yeah? This part's the part that defines a singularity, and this thing is a nice holomorphic function. Yeah? And the highest order non-zero coefficient of this thing will be the biggest blow-up part of it, right? Yeah, that'll define how quickly it's blowing up. But strangely, that's not the most important term of this singular part. It's not the most important term. But if we're just interested in how quickly it's blowing up, it depends on which of these guys is non-zero. Yeah? If a to the minus n is non-zero, then we're blowing up like 1 over z minus z0 to the power n. Yeah, and all the other terms are not blowing up as fast. If this guy's the first non-zero term, then we're blowing up like 1 over z minus z0 to the n minus 1. Yeah? You see what I mean? So this part is called the principal part. It's called the principal part. Yeah? And the first non-zero term is called the order of the pole, because it defines how quickly the thing is blowing up. Yeah? Cool, but that stuff we will get to later. The point of this calculation is just to show you that we can quickly understand the nature of this guy, the nature of the blow-up from this kind of thing. All right, cool. So, yeah, all right. We wrap it up now. Have a great rest of your day, and see you all next week.